Hello everyone, we want to continue our marathon in three-dimensional geometry with equations of planes. So we have our system of x and y and z axis, we have the origin, and there is a plane in 3D space, just like, for example, this book right now, it's in the space of this room, so it can be in any form, any shape, just randomly located in the space. That's the plane. And we have a point P. We have a particular point P naught, a particular point P naught, P sub 0, which is given, and the coordinates of this point are clear. We know that the plane is passing through this point, and the position vector of this given point is vector r sub 0. And then we consider another point P on the plane, arbitrarily chosen, with any kind of x, y, z coordinates. And that point on the plane has a position vector for itself as well. And that would be vector r, or vector OP, basically. And if we connect point P sub 0 to point P, then that would be a third vector completing a full triangle. So we can say vector OP0 plus vector P0P is equal to vector OP, which is the famous triangle law in vector addition, actually. And we can, of course, instead of OP, write vector R. Instead of OP sub 0, we can write R sub 0. And we have vector P0P. But the thing is that if you consider only one vector P0P, there are millions of planes that are passing through this vector, and they contain this vector. And there's millions of those planes. Imagine, for example, the edge of this book to be that vector P0P, okay? So this is one plane, this is another plane, this is another plane, this is another plane, that's another plane. So you see that there's millions of planes that could pass through this vector and can actually contain this vector. So we see that only one vector is not good enough to identify or specify that particular plane in 3D space. So that means that we need to have at least two vectors, so that we can pass a plane containing those two vectors, so that we can identify a plane with. With one vector, you can have millions of planes actually. There's millions of planes in space that contain this vector. But when you have particularly two vectors, in that case, there's only one single plane that contains both of these vectors. So that gives us the idea of breaking down vector P0P into two vectors. One would be vector SB, and the other one TA, where S and T are just scalars. So we're considering two vectors, vectors A and B, and these are called direction vectors of the plane. In the past, we had one direction vector for the line, but now we have a plane, so we have two direction vectors. One is vector A, one is vector B. Now, a multiple of vector A would be vector TA, where T is a scalar. A multiple of vector B would be SB, that vector. S is a scalar. And when you add SB with TA, that gives you actually P0P. So in that case, we will be able to identify very clearly that one single plane that we have in space. We want to identify. So instead of P0P here, I need to break it down into two vectors. One would be vector T times vector A, and the other one would be S times vector B. And T and S are, of course, scalars, right? So this is called the vector equation of this plane. So I'm going to write that down here. So vector R equals R sub 0 plus T times vector A plus S times vector B. And the T and S are both real numbers, okay? Vectors A and B are known as direction vectors of the plane, as I said. Now, this vector equation of the plane can be written in Cartesian or algebraic form. So we can write vector x, y, z, which is actually the position vector of that so-called arbitrary point P on the plane, whose coordinates were x, y, z. So that would be replacing vector r. And then r sub 0 would be x naught, y naught, z naught, which is the position vector of that point P sub 0 with coordinates of x naught, y naught, z naught. And then plus t times, now instead of vector A, we can, of course, write its components. So we can call them A1, A2, A3, and for the other one, B1, B2, and B3. Okay, so B1, B2, B3 are the components of the direction vector B. A1, A2, A3 are the components of the direction vector A. T and S are real numbers. So these two are actually vector equation of a plane in 3D space. From the vector equation, we can always derive a series of equations known as parametric equations of the plane. So imagine if I simplify the right side, okay, I have t times a1 plus s times b2. If you do the math, you get t times a1 plus s times b1, and then you add it with the first component of the vector r sub 0, which is x naught, and that would be the x component of vector r on the left. So that would be x equals x naught plus ta1 plus sb1. If you expand, and simplify the right side, you will get this result. And if you set the second components on the left side, right side equal to each other, you would get y equals y naught plus ta2 plus sb2. And by setting the z components of the vector on the left side and the right side of the equation, you get z equals z naught plus ta sub 3 plus s times b sub 3. So these three scalar equations combined together represent the parametric equations of the plane in 3D. So vector equations, okay, both in Cartesian algebraic form and the standard form, and the parametric equations are derived here. Now we want to do some numerical example. It says write the equation of a plane, okay, passing through 3 points ABC. If I have 3 points, just like a triangle, it would look like something like this. This is a triangle in the space, or this one, or this one, or that one, or this one, or this one, or that one. These are all 3 arbitrarily selected points in the 3D space of this room, and those 3 points make a plane, make a triangle in the space. And we want to write the equation of that plane, okay? So in order to do this, what do we need? We need 2 direction vectors instead of 1. In case of lines, we needed to have 1 direction vector. Now we need 2 direction vectors. So I'm going to select these direction vectors, vector AB, which is x of b minus x of a, y of b minus y of a, z of b minus z of a. So that gives me -3 minus 2, which is -5, 1 minus 0, which is 1, and 4 minus 1, which is 3. So this is one of the direction vectors. I'm going to call it vector A. And vector B, I'm going to select a vector AC. So x of c minus x of a, I'm writing the formula. And z of c minus z of a. So 0 minus 2 is -2. 0 minus 0 is 0. 7 minus 1 is 6. So these two can play the role of 2 direction vectors of the plane. And now we have those 2 vectors. We need a point on the plane. Now I have 3 points instead of 1 on the plane. I can select any of them, okay? So I'm going to write the equation as x, y, z equals, I will select point B, -3, 1, and 4, that with the coordinates, plus t times the first direction vector, -5, 1, 3, plus s times the second direction vector of the plane, and this becomes the vector equation of this plane. And of course, always we have to say that t and s are scalars. Now, instead of -3, 1, 4, I could have chosen the other point, 0, 0, 7 or 2, 0, 1. As you see, the equation of a plane is not unique. You can have any point on the plane selected. I can write the parametric equations right now by a simple conversion. So the left side is x, y, z. The right side is -3, and then if I multiply -5t and -2s, that will be the first component, 1 and 1t, and 0, so we don't bother, and then 4 plus 3t, and then we have 6s plus 6s. So if you simplify the right-hand side of this equation using operations with vectors, you end up with this vector, and then you see that left side vector will equal to right side vector when components are equal to one another. So x should equal to -3 minus 5t minus 2s, y should equal to 1 plus t, z should equal to 4 plus 3t plus 6s. So this becomes the parametric equation of the plane that contains the 3 points. Write the equation of a plane containing a line, this line, R1. So containing this line, R1. So this is R sub 1. Okay, and this is R sub 2, which is supposed to be parallel to the plane. So again, we have a plane, and we have a line which is on the plane, as you see here. Okay, it's on the plane, and we have a third line which is parallel to this plane. Imagine this is parallel, this is parallel, that is parallel, this is parallel, this is parallel, this is parallel. So all of these lines are parallel to the plane. So one line is R2, the other one is R1. R1 is on the plane, okay? And we want to write the equation. So the question is, how can we do this? We need to have one point on the plane, and the point on the plane we select is going to be a point that is on the line R1. So I'm going to select point A, which is 0, 3, -5, and I have to find two direction lines. One of them is easy. That's the direction vector. Sorry. One is the direction vector of line R1 itself, which is 6. So 6, -2, -1. Okay. So this is one direction vector. I need a second direction vector. If I find this second direction vector, then like before, I can write the equation. So the question is, how can we find this second vector? This is the question we have to answer. If we can find a second vector, okay, on the plane with this first vector, then we'll be totally fine to write the equation of the plane. Now this line itself has a direction vector by itself, right? And that is 1, -3, -3. So 1, -3, and 3. So this is basically the direction vector of the line parallel to the plane, okay? And that would have, that vector would have a vector parallel to itself, but, on the plane, and it would have the same coordinates, or a multiple of those coordinates. So some vector that is parallel to this direction vector of the line, and it's perhaps a multiple of that, could be considered on the plane. So one vector is on the plane, one vector is on the line, and these two are parallel. They are collinear vectors. One is a multiple of the other. So I can choose that vector 1, -3, and 3. And with these two vectors and 1 point, I can write the equation of the plane. So that will be vector x, y, z equals 0, 3, -5 plus t times the first direction vector plus s times the second direction vector. So that is the vector equation of the plane. And of course, you can convert this into parametric form as we did in the first example. I will try to give you more examples in future about how we write equations of planes. One more thing I have to add here, and that's the third form, which is called scalar equation of a plane, and that is like this: ax plus by plus cz plus d equals 0. This equation is known as scalar equation of a plane, and it's used a lot. And these numbers a, b, c are actually the components of a vector n, which is called the normal vector of the plane. So if you have a plane and you have a vector which is perpendicular to the plane, it's called the normal vector of the plane, and its components are always a, b, c, which are the coefficients of x, y, z in this equation. Okay, so remember vector equation, parametric equations, and scalar equation of a plane. All right. This is the form: ax plus by plus cz plus d equals 0. A, b, c, d are just integers, okay? And we'll do more examples in future.